Introduce the golden age of TV game shows. Let's Make a Deal was a real
Monty
gem,
Hall,
wasn't it? The maestro of surprises. Became famous not just for his hosting skills, but also for sparking a whole new kind of dilemma in probability theory. Picture this. You're on the show, facing three doors. Behind one, a shiny new car awaits, while behind the others lurk goats. Yep, goats. You pick door one, hopeful and trembling with anticipation. Then, in classic Monty style, he swings open door three, revealing yet another bleeding goat. Now, here comes the twist. Do you stick with your gut or take a wild swing and switch to the unopened door? It's like a math problem meets a guessing game meets a farmyard fiasco. So what's your move, contestant extraordinaire? Possible outcomes. To tackle Monty Hall problem math in a more humorous way, instead of laboriously counting which option leads to the car if you stick or switch. We could easily compile a chart for this. Let's say you pick door number one. Without loss of generality, then the outcomes can be described as follows. Sure thing, sometimes it goes like this. In 2 out of 3 cases, you win the car by changing your selection after one of the doors is revealed. This is because there is a greater probability that you choose a door with a goat behind it in the first go, and then Monty is guaranteed to reveal that one of the other doors has a goat behind it. Hence, by changing your option, you double your probability of winning. Another way of seeing the same set of options is by drawing it out as a decision tree, as in the following image. Using Bayes' theorem, the Monty Hall problem math is like a mind-bending magic trick that leaves everyone scratching their heads. First off, why does the math play tricks on us? Why does sticking to your first choice feel like betting on a one-legged horse in a three-legged race, while switching doors suddenly turns you into the odds-on favorite? And then there's the randomness of it all. If Monty's just randomly flaunting goats, shouldn't our odds be as scrambled as a Rubik's Cube in a hurricane? Enter Bayes' theorem, the Sherlock Holmes of probability theory. It's like having a mathematical Watson guiding us through this bewildering maze. With Bayes at the helm, we can decode the Monty Hall conundrum like a seasoned cryptographer decrypting ancient scrolls. It's all about updating our bets based on the evidence, turning what seems like a game of chance into a strategic game of cat and mouse. So next time you're faced with Monty and his tricky doors, just remember, Bayes has got your back, turning goats into gold with the flick of a formula. Let H be the hypothesis, door 1 has a car behind it, and E be the evidence that Monty has revealed a door with a goat behind it. Then the problem can be restated as calculating PHE, the conditional probability of H given E. Since every door either has a car or a goat behind it, the hypothesis, not H, is the same as door 1 has a goat behind it. In this case, Bayes' theorem states that the problem as stated says that Monty Hall deliberately shows you a door that has a goat behind it. Breaking down each of the components of this equation, we have the following. PH is the prior probability that door 1 has a car behind it without knowing about the door that Monty reveals. This is 1/3. P note H is the probability that we did not pick the door with the car behind it, since the door either has the car behind it or not. PEH is the probability that Monty shows a door with a goat behind it, given that there is a car behind door 1. Since Monty always shows a door with a goat, this is equal to 1. PE not H is the probability that Monty shows the goat, given that there is a goat behind door 1. Again, since Monty always shows a door with a goat, this is equal to 1. Combining all of this information gives the probability that the car is behind door 1 is completely unchanged by the evidence. However, since the car can only either be behind door 1 or behind the door Monty didn't reveal, the probability it is behind the door that is not revealed is 2/3. Therefore, switching is twice as likely to get you the car as staying. Variant, the random Monty Hall problem. This result depends crucially on the fact that Monty was always guaranteed to open a door with a goat behind it, regardless of what door you picked initially. That is, PIH, PI not H. Now consider what would happen if Monty randomly opened a door we did not pick and it contained a goat. What is the probability that our first pick is correct, regardless of which specific door we picked? In this case, PEH, The probability that Monty will show us a door with a goat behind it, given that our first pick was correct and does have a car behind it, is still 1. If you pick the door with the car, the 2 other doors are guaranteed to have a goat, but P changes. This represents the probability that Monty picks a door with a goat behind it, given that your original choice of door had a goat behind it. In this case, Monty chooses randomly between one door that has a goat behind it and one door that doesn't have a goat behind it. Therefore, the probability that he picks a door with a goat is P(H)(1F). Laying this out, we get there is a 1/2 or 50% chance of our first pick being correct when Monty randomly opens a door and it happens to have a goat behind it. The naive reasoning that fooled so many mathematicians works in this case. That's it. We already explained Monty Hall problem math. If you have any questions or suggest some topic, please leave a comment. We read all the comments of your guys. Thank you for watching until now. Like, subscribe, and turn the bell button to get notices when we release new videos. Goodbye.